Hello, welcome to this video on circle theorems. This is literally just going to go through what the circle theorems are that you need to know for iGCSE. And then I will make a separate video kind of going through some examples and how you use them in an exam style question. But this one is just going to go through what they are. You should try to make your own notes from this. It's a good video to revisit if you forget one of them, or if you just need a reminder of what the circle theorems are that you need to know. There are 11 different things that I'm going to go through in this video, so there are a lot and you do need to remember them. Like, there's something that you need to memorize for your exam. They won't be given to you. You need to know what they are. You need to know the wording. If you are asked to explain your answer or give a reason, you have to know the wording of each of the rules to be able to write it into an exam question. Okay, so it is a lot. It's a lot of memorizing, which only comes with practice and what's the word I'm looking for, like repetition, especially for remembering what they are. A lot of, sticking them up around your room and revisiting them a lot just to remind yourself what they are. You do need to know them kind of inside out. So just to start off, I'm going to do a really quick recap of the different parts of a circle. I'm assuming we know most of these anyway, but just to refresh our memories, obviously I am assuming that you know that the radius of a circle goes from the centre to the circumference, and the diameter goes all the way across the circle through its centre. I should have made it clear where the centre was there. So this would be the centre of our circle. So diameter goes all the way across the centre of the circle, and radius goes from the centre to the circumference. If we don't know that by now, we're maybe not ready for circle theorems. You need to go back and do area and circumference of a circle. But for everyone else, I'm assuming that we know those two parts of the circle. The other ones which you might not remember are things like a tangent. So tangent is this line. It is on the outside of a circle. So whilst I'm calling it part of a circle, it's not actually inside the circle. It is a line on the outside that touches the circumference of the circle only once. So it touches in one place and it is on the outside of the circle. We also have a chord, which is on the inside. Tangents and chords we will be using a lot throughout circle theorems, so you do need to know what those two things mean. And a chord is a line that is inside the circle. It hits 2 points on the circumference. So you can see this one is hitting here and here, but it does not go through the centre, okay? Or it doesn't necessarily go through the centre. That is a chord. And then an arc is a part of the circumference, which you should remember from when we did the length of an arc and area of a sector and things like that. And we looked at arcs of circles then, but it is a part of the circumference. The last two are sectors and segments. Sector is your pizza slice. So a sector is bounded by 2 radii, which is just more than one radius. So this would be a radius, this is a radius, and when you have those two things, it creates a sector, which looks like a slice of pizza, whereas a segment is made by a chord and the arc, the part of the circumference that it creates is a segment. So a segment doesn't pass through the centre or doesn't include the centre of your circle. That is a segment. So those are your key pieces of terminology. We will use a lot of this as we go through the 11, again, I know 11 is a lot, circle theorems that you need to know. So here's our first one. So the first 3 are quite straightforward. They would be a grade kind of 5. Could potentially come up on a foundation paper. After that, once you get into the ones later on, they are grade 7 and they would more typically come up on a higher exam paper. So the first one that you need to know is this one, where you have a tangent and a radius. The angle created when they meet is 90 degrees. So here is your tangent, here is your radius, and you can see where they are meeting here it creates a right angle. That one's quite easy to spot, and comes up quite a lot. You'll use it in lots of different ways. It's actually used when we have an example or a question, including the circle theorem underneath. So this is your second one. When you have two tangents, these are these lines on the outside, but they are coming from the same point, which would be this point here on the outside. So those two tangents are starting from the same point, and they are meeting the circumference at different places. So the top line meets the circumference here, and the second line meets the circumference here. They are the same length. So those two tangents are the same length, or at least they are between where they meet the circumference and the point where they started from. So that line is the same length as this line, okay? We can kind of expand on that. If you then join that up to the center of the circle, you have a right angle, obviously, using the previous circle theorem. So the radius is meeting a tangent, so we are getting a right angle here. And because the lengths of the lines are the same, it actually creates a kite shape. Okay, now a kite is just a quadrilateral. You know that this is 90 degrees, this is 90 degrees. We might be able to use this angle in the middle here. We might be able to use this angle over here. We could also join the center of the circle up to the point where our tangents have started, and that would give us two right angled triangles. There's lots of ways that can then be used within an exam question. But the main point is that when you have a tangent starting from the same point, they are the same length, even if they meet the circumference at different places. Okay, so two tangents from the same point have the same length. Wait, the third one, tripping over my words. The third one we need to know is that the perpendicular bisector of a chord passes through the center of a circle. So here's our chord, this line here. It's a chord because it is meeting the circumference at two places. And if we find the perpendicular bisector of that, now a perpendicular bisector is a line that cuts that chord in half. That's the bisector part of it. If you're bisecting it, you're cutting it in half into two equal pieces. And it's perpendicular because it is it's crossing it at a right angle, which is why we have this right angle here. So this line here is the perpendicular bisector. It is cutting our chord in half, and it is meeting it at a right angle. That line, so the bisector has to go through the center of the circle. So if we continue it so that it's from the center to the circumference, it would be a radius. We could even extend it all the way out and it would become a diameter. But because it is a perpendicular bisector of a chord, it has to pass through the center of the circle. That is the key point. So if you have a chord, you perpendicularly bisect it, it has to pass through the center of the circle. Okay, the fourth one, number 4, is this one that looks like an arrow. You'll often hear it in different videos and things being referred to as the arrowhead theorem. Do not call it that in an exam. You wouldn't get any marks. That's not its official name. But if the shape of it helps you remember the rule is that the angle at the center of the circle, so this one here, which I've labeled 2A, is twice or 2 times the size of the angle created at the circumference. The key point is that those two angles come from the same 2 points on the circumference. So we've started them here, okay, and we've joined those 2 points up to the center. If I kind of go over it, the pink part is joining up to the center, and then from the same 2 points we have also joined it up to the circumference, which would be these 2 lines here, which I've just gone over in the dark blue. The angle created at the center of the center of the circle is 2 times as big as the angle at the circumference, which is why the angle at the centre is called 2A, and the one at the circumference is A, because at the centre it is twice as big as the one at the circumference. There is some kind of fancy terminology around this. You might hear it saying that the angle subtended at the centre is twice the angle subtended at the circumference. Subtended is just a fancy way of saying the angle made at the centre is twice as big as the angle made at the circumference, but they'll often use the word subtended if you read that like in a textbook or in other videos, but just so you're aware of that terminology. You don't have to use the word subtended when you are writing a reason in an exam. It is enough to say that the angle at the centre of the circle is twice as big as the angle at the circumference. That is kind of the wording that you need to say. Your keywords being angle, obviously, but centre of the circle and this angle at the circumference. Yeah. Okay, circle theorem number 5, and this one is linked to the previous one. The angle in a semicircle is 90 degrees, which kind of fits a semicircle. The angle at the centre, so this angle here, is a straight line, so it's 180. So half of that to find the angle at the circumference is 90, which is a right angle. So the angle in a semicircle is 90 degrees. So obviously this would be a diameter at the bottom, at the base of the semicircle. So we cut it in half and then join to the circumference. So at any point, wherever we join to the circumference, I've drawn 2 examples here, but obviously that angle could be anywhere on the circumference, but it is always 90 degrees, even if I drew in a third one. So if I did it up here, as long as it is joining, the base of that is the diameter. This angle here is always going to be 90 degrees. So whenever there is a semicircle, so the circle is split by a diameter, any angle created in that semicircle would be 90 degrees. Okay, and again, it's based on that rule that the angle at the centre is twice as big as the angle at the circumference. This time the angle at the centre is 180 because it is a straight line. That means the angle at the circumference has to be 90. Okay, this one, again, sometimes you will hear this referred to as a bow tie theorem. Again, please don't use that word in an exam. It's not its official name, but it kind of looks like it's making a bow tie. And this the rule is that angles in the same segment are equal. What's happening here is that we have 2 points on the circumference, so these 2 points, and they have created 2 different angles from those 2 points, okay? So when it's saying angles in the same segment are equal, this is your segment, so this part that we've created by joining the 2 points up or by drawing the chord, and by that I mean this chord here. This pink line is our chord. If we then create angles from that chord, the angles would always be the same size. So these 2 angles B have both been drawn from those 2 points. So you can see we've used these 2 lines and that gave us angle B. And then if we did this from the same 2 points but to a different place on the circumference, so here, just make that a bit clearer. So they're both, that pink kind of triangle is still starting from the same 2 points on the circumference. Therefore, the angle it creates is the same size as the first angle we created with the blue lines, the dark blue lines. Okay, so angles in the same segment are equal. Again, we could say that we could use the word subtended in there and say angles subtended from the same chord or angles subtended from the same segment are equal to each other, but we don't have to use the word subtended within our working or within our wording because, like I say, it's just a fancy word, a fancy way of saying that it is the angle made at that segment from those points, okay? Yeah, so those two angles would be equal to each other. The same would work if we went the opposite way around. So we could, can I change colours? If I go green, I could go on the other side of that chord as well. So I could go into that yellow segment and create some angles. So if I start from the same 2 points again, oh, I didn't realise I was going to draw a straight line. Hang on. So if I start and go to the circumference there and join it back up, and then I could do it in a slightly different way. If I use pink again, I could go like this. Okay, so again, I've drawn two kind of triangles coming from the same two, starting from the same 2 points. And that would mean that this pink angle here and that green angle there would be the same size. Whatever the pink one is would be the same size as the green one, because they have started from the same 2 points on the circumference and created a third point somewhere else on the circumference. And the angle created at that third point is the same wherever that third point is. I hope that makes sense. Like I say, I will do a second video. Please make sure to watch that. I will do a second video where we use these in an exam question. But for now, I just want you to make notes and start to learn and memorize the different circle theorems that you have to know. Okay, number 7 is my personal favourite, is the cyclic quadrilateral. That's why it's my favourite, because I enjoy saying cyclic quadrilateral. What that means is if you have a circle and you create yourself a 4-sided shape within that circle where each of the vertices of your quadrilateral are touching the circumference of your circle, it wouldn't work. If I just go back to the blue, it wouldn't work if, so there's your circle, if I then drew a 4-sided shape like that, because this point here is not on the circumference. All 4 points, all 4 corners, all 4 vertices of your quadrilateral have to be on the circumference of your circle. That is what makes it a cyclic quadrilateral, because what you've essentially done is joined all 4 vertices up with a circle. That is what creates the cyclic quadrilateral. And the rule is that opposite angles add up to 180. So for this example that I've done, if I just rip this off, for this the diagram that I've drawn, we would have A and C are opposite to each other, so they would add up to 180. And angles B and D are opposite to each other, so they would also add up to 180. So opposite angles in a cyclic quadrilateral, it is really important that it is a true cyclic quadrilateral and that all 4 vertices or all 4 corners of your shape are touching the circumference of your circle. Otherwise, this doesn't work. But as long as it is a true cyclic quadrilateral, the opposite angles will always add up to 180. Okay, we're nearly there. This next one is arguably the most difficult. It's the one that's trickiest to spot. It's the one that people try to use and often get wrong. So this one is one where we'll practice this a lot and practice spotting it in exam questions and things. It's called alternate segment theorem. That is enough in an exam for your reason. So you could say angle B is equal to the other angle that I've labelled B because of alternate segment theorem. But what it is, obviously you need to have an understanding of what that actually means. So what it means is that the angle between a tangent and a chord. So you can see that here. So here is my tangent and here is my chord. I sound like a nursery rhyme. It's like, here, I'm a little teapot. Here's my tangent. Here's my chord. But those are the first 2 points that we need. So we've got a tangent, we've got a chord, and they are creating an angle. The first place that people get confused is they mix this up with the very first one that we looked at, and they want that angle to be 90 degrees. Okay, remember that this is the angle between a tangent and a chord, not the angle between a tangent and a radius. A chord and a radius are two different things. The angle between your tangent and your radius is 90 degrees, and they'll often kind of add that into an exam question, so you might have to use both. But the angle between the tangent and the chord could be anything. It doesn't have to be 90 degrees because a chord is not a radius. Obviously, they're two different names. You wouldn't name the same thing twice. A chord and a radius are different, so the angle between a chord and a tangent is not 90 degrees. Okay. Just wanted to get that cleared up first. So the angle between the chord and the tangent is equal to the angle in the opposite segment. So we are saying that the chord we have started with, this pink line that I highlighted, has created this segment of the circle, okay? So this is the segment that our chord has created, this yellow part. The opposite segment is the segment created on the other side of that line. Blue's not the best colour because everything's already blue. Let's use this peach. So all of this part of the circle is also a segment. It's actually the major segment, and the little yellow one is the minor segment. Whenever we draw a chord on a circle, we are creating two segments, a big one and a small one. So the chord we've drawn, the opposite segment is the other side. And from there we can create an angle. So we have created an angle by drawing two lines from, if I stick to this orange, we've created an angle by drawing two lines from either end of that chord. So obviously our chord is meeting the circumference at these 2 points, okay? And we've then used those 2 points to create an angle on the opposite side of the segment, which is where this angle B is. That angle B that we have created is the same size as the angle that we are getting between the tangent and the chord, which was this original angle B here, okay? Now, from my explanation there, you can probably see why this is the most difficult one to use. Key things where people get wrong. So the first thing is that they confuse it with the very first theorem. So they confuse it for the angle between the tangent and the radius is 90 degrees. Okay, don't do that. The second way that people get confused is that they forget that this angle B goes all the way from the tangent to the chord. So that means it goes outside of the circle, okay? Don't be fooled. Don't try and work it out so it's smaller than the tangent, okay? That angle is measured all the way from the chord. So all the way from here through the circumference of the circle to where the tangent is. That angle is measured from inside the circle to outside of the circle, from the chord to the tangent. Okay, and then the third part is then struggling to identify what the opposite angle is. Where the angle in the opposite segment is. Okay, so once you've got your chord, you've got your tangent, what you are looking for is two lines that are starting at either end of your chord and then joining together. That is where the equal angle is created. Okay, again, it is the most difficult one. I will go through it in a separate video, how we use it and how to spot it in an exam question. For now, we just need to familiarise ourselves with this diagram so that hopefully we can spot it a bit easier if it comes up in an exam question. Okay, we have two more and then a kind of extra one that has been kind of lumped in, but I'll get to it in a minute. So number 9 is actually intersecting chord theorem rather than a circle theorem. So this is all to do with lengths and what happens when you have chords that are crossing each other. So this first one is where they cross on the inside of a circle. So obviously we have called that internal intersection because the two chords are intersecting or crossing each other inside of the circle. When we have that happen, we've given the point where they intersect a name. We've called that E. and then we have chord AB and we have chord CD. If we take the two parts of that AB line, so from A to where they cross at E, and then from E to B, if we take those as two separate lengths and multiply them together, we get the same as if we multiplied from C to E by E to D. We get the same answer. So if we multiply AE by EB, we get the same answer as if we did C to E multiplied by E to D. And again, we'll have a look at that in a question later on, but we're usually going to have to do some kind of rearranging there. You might have different parts given to you and ask to find a missing part, and there's usually some kind of rearranging of that equation to do to find whatever we need that's missing. But again, we'll have a look at that in the next video. The second intersecting chord theorem is external intersection. So this one we have two chords A, B and C, D again. This time they're not crossing inside of the circle. They're two totally separate chords, but if we extend them both to outside of the circle, eventually they will cross, unless they were parallel to each other, but these aren't. So if we take the two chords and we extend them outside of the circle, eventually they will cross at this point E. And very similarly to the last one, we are looking at different parts of that line multiplied together gives us the same as the other one. So this time we're going from A all the way to E is times by B to E. So each time we're going to the point where they're meeting outside of the circle. So A to E multiplied by B to E is the same as if we did C to E multiplied by D to E. And again, in an exam question, you're probably going to have to rearrange that in some way to find a missing value. And we'll have a look at that in the next video. So again, familiarise yourself with the diagrams, with these formulae. So this one and this one, so make sure you know those. And then we'll have a look at how we can apply them in an exam question in the next video. And then the last one, I've put it at the very last, not because it's the most difficult, but because technically I don't class it as a circle theorem. This is just something that you should be aware of from your knowledge of like radius and types of triangle. So if you have two radii, which again is just the plural of radius, if you have two radii, they make an isosceles triangle, because obviously the radius, no matter where it is, no matter where it's meeting the circumference, it's always the same length. Okay, so they won't necessarily, in an exam question, they won't tell you that these two lengths are the same using the usual terminology, the little lines. But you know that they are both radiuses or radii because they are coming from the center of the circle. So they have to be the same length, which means that these two angles at the base of the isosceles triangle are also the same size, because base angles in an isosceles triangle are equal to each other. You will have to use that quite a lot in a circle theorem type exam question. Yeah, there's not much more to say about that. You will have to use it a lot. And like I say, they won't make it explicit that those two lines are equal to each other. You are expected to know that because you can identify that those two lines are both radii. Therefore, they have to be the same length because they are both a radius of the circle. Okay? Yeah, right. That's the last one. Yeah, I don't have another page. So make sure you go over those, familiarise yourself with the diagrams, what they look like, what type of angles you are looking for, and then after you have had a good look and a good revise of these, then move on to the next video so you can see how those theorems are applied to an exam question and how we can use them to find missing angles, lengths, whatever it may be, within a problem. Okay, I hope that made sense. Please make your own notes from this video. Stick them up all over your bedroom, you know, wherever you're going to see them all the time, so that you are getting that constant repetition of them, so you can remember them, because they're like 11 different theorems to learn. That's a lot, and that's just for this topic. Obviously, you also need to know all your usual angle rules, you know, angles and parallel lines and things. So the more ways you can come up with to make sure you remember these 11 circle theorems, the better. Okay, hope this helped. Have a lovely day. Thank you for listening to this quite lengthy circle theorem video. Bye.